Hi, this is Andrew McLaren. We're going to talk about equilibrium and ice charts today. We're going to do that by looking at some prerequisite skills that you're going to need, including identifying these symbols. There's a lot of different versions of K, and some things are similar but slightly different than K. So we're going to spend some time talking about that. Then we'll go over the main idea, help you build that conceptual understanding, and some simulations to help with that as well. Then we're going to try and do some actual problems that you do with an ice chart. And we'll go over like typical easy ice chart problems with negligible x's, as well as harder ones where the x might be significant. And we'll briefly talk about acid and base. I'll hold off on that for the other unit, going off more in depth, but I wanted to talk about it because it's related to K equilibrium. So by the end of this, you should be able to write out a K equilibrium from a reaction. You should be able to explain what it really is, and you should be able to solve problems involving equilibrium and K and solubility and gases and acids and bases, all that. Okay? When we're working with these problems, there's a fair amount of math that you need to be comfortable with to be able to do K equilibrium. Like you need to be able to do order of operations and complex fractions, as well as scientific notation, kind of like this, because a lot of the formulas that you're going to work with, you're going to need to find an x value, and it's going to look very much like this format where there's things that are being multiplied. There's some numerator denominator. There's also some exponents up there. So it's really critical that you have those skills down to be able to do equilibrium problems. You're also going to need to be familiar with a balanced reaction and thinking through what that really means in terms of the molecules that you're working with. And you're going to need to know like moles, molarity, concentration, pressure, and to some extent gas laws. That comes into play oftentimes with like partial pressure. Um, so it's something that's relevant, but it's not like super critical. So that's the main like math and content that you're going to need to know. Now, specifically when we're talking about equilibrium, when you have a reaction, there'll be oftentimes on the left side and right side um, these chemicals. And then in the middle, you're either going to have this or you're going to have something that looks like that. In reality, these things aren't 100% going to the other side, but we can say just for like simplicity's sake, it is. Like maybe 1 in a million reactants are staying as reactants, but like 999,000 of those reactants are going to turn into product of the million, right? So a vast majority will turn into product. So we can usually say that's just 100%. That makes it really easy when we are working with like equilibrium, because that's basically not something where you'd think about like a K value. It's just make it be all whatever it is that you're making, right? This, when you have the backwards and forwards arrows, which is sometimes shown as like with only one line on the arrow, this is when we're at equilibrium. This is somewhere in the middle. There's like a little bit of reactant, a little bit of product. It's not 100% product. It's not 100% reactant, but somewhere in the middle. It's when we've reached an equal rate forward and backwards. So the oftentimes people will talk about products being on the right side of the reaction and reactants are on the left side of the reaction. And so you'll see products P written on the right side and reactants on the left. And like I was saying, this is equilibrium is all about when the forward and reverse rates are equal to each other. If you have more reactant, for most things, that's going to make that forward reaction go faster. But if you've got a lot of product, it's going to make the reverse rate go faster. So as the reactants get used up, like if as more products are made, the forward rate slows down, right? So yeah, it's producing product, but it's slowing down the rate that it's producing that product. And as more product is made, the reverse rate actually increases. And so yeah, you might start off with one situation where you're mostly like reactants and turning into product. And while that's happening, it's slowing down that process until it reaches enough product and it's getting pushed back enough where like the backwards and forwards rates are equal to each other. And at that point, it's kind of like I like to think of like a treadmill. Like if you're running forward at like 2 meters per second, treadmill is moving backwards at 2 meters per second, net change of 0 meters per second. You're like running still on the treadmill, right? They're canceling each other out. So you can think of that as the forwards rate and the reverse rate. Now, if you have a like initial condition where the forwards rate is faster, you're going to move to the right. You're going to make more products. And if you have something here where you've got too much product and not enough reactant, the reverse rate is going to be really, really fast. So it will be going backwards in those situations. So if the reverse rate is winning, it'll push you to the left. If the forward rate is winning, it'll push you to the right. That's the general idea here. And then K, this is just a ratio of products to reactants. So it's oftentimes written as P over R, and this is the amount of stuff. I'm going to go a little bit more into detail, but that's the general idea. So it's like, oh, there's a little bit of product, there's a little bit of reactant, right? And then there's all these different versions of K that you've probably seen, like KSP, KP, KA, KB, KW, and then like little Ks. Those also come into play. So for the most part, all of this is not the little k, but all of these things are basically the same sort of idea. They're all ratios of reactants and products, but they're for like slightly different like chemical situations. Like we have the subscript SP. That's when we're talking about solubility. So it's something that's like a salt that's dissolving into water. And it's all about how much product it can really make. It doesn't matter how much reactant you have. We don't include solids in K values. I'll talk a little bit more about that in a little bit. But it's all about the solubility of the product, like how much product can we make? How much will this water take salt in, for example? Gases, this is a pressure, so it's measured in pressure. This is very, very similar. Uh, like solids don't really matter in a solution because they're not really taking up space. They're just in the bottom. Same thing with solids and liquids for gases. They don't really take up much space in like a room. And so like they're not going to really affect K equilibrium. So they're not included. And then acids, Ka, this is when we're talking about acids. Kb, this is when we're talking about bases. And then Kw, this is the equilibrium for water for its dissociation, turning into H plus and OH minus. And then little k, this refers to, this is like a lowercase, these are capitals. Sorry, I know handwriting is kind of hard with that. But lowercase, this is talking about the rate constants, like the forward rate and the backwards rate. And so they'll oftentimes give subscripts on these like kf and kr or k1 and k minus 1. And it's, you don't really need to know this. This is something that you're going to really see more like in an AP Chem or a college chem. But these rate constants, if like the forward rate is faster in general than the reverse rate, you're gonna have a big K, right? So this is a constant. The actual rate does depend on the amount of the stuff, but we can look at rate constants and determine like, oh, if the reverse rate in general is more powerful than the forward rate, you're gonna have a small K value, which kind of makes sense because if it's a very powerful reverse rate, you're gonna be making a lot of reactants. And so you're going to have very little products and a lot of reactants in a small K value. For the most part, what we can say is K is equal to P over R. And so you can also look at the reverse reaction. So this could be for like one reaction, like reaction 1, and then this is like the reverse of that reaction. And it's kind of weird. But if you are looking at the reverse reaction, like if instead of going from A to B, you're going from B to A, you just do the inverse of the K value. Like if this has a K value of, let's say it was like 10 up to the third power, this is going to have a K value of 1 over 10 up to the third power, which is 10 up to the negative 3. This is very small. This is very big. So if you have one reaction going forward, its reverse reaction, you can look at like the K value and you can literally see it's like B over A and A over B. You've flipped the A and the B values. So you just flip the value of the K, you make it its inverse. And that should give you the K value for the reverse reaction. Be careful. That's not really the case for Ka and Kb because they aren't reverses of each other. They're close. They're very, very close to being like opposites of each other. They're not the exact opposite reaction. Like Ka makes, and don't worry, if you're like acids and bases, that's usually taught after equilibrium, but I just wanted to do this as a review video. And so if you have seen acids and bases, this will be useful. If not, this is just like a little preview, okay? In any case, acids make these protons, bases make these hydroxide ions, and so you get Ka values that look like that, and Kb values that look like this. And actually, if you multiply Ka times Kb, you get Kw. So these things are related through Kw. They're not like inverses of each other. And you can see, like, I haven't literally just flipped the numerator and the denominator. I've got an OH and an H here, so they're different things I'm working with there. Now, if you wanted to, you could, like how these kind of cancel out, you could cancel out things like this. Because you can say like K1 times K negative 1 is going to equal 1. Because this is basically saying, I think K1, let's say, was B over A. And then this is A over B. You can see that no matter what the numbers are, they should cancel each other out, kind of like that. So that's why Ka and Kb are slightly different than like the reverse rate. It's because they're related through Kw, through this dissociation constant and the amount of these things that can be made by water normally. They're not simple inverses like that. So you just got to be a little bit careful with those. Yeah. So I forgot one of my vocab words. I want to also go over Q. Q is very similar to K because it's also a ratio of products over reactants. But what's different is that this is not at equilibrium. This is a ratio of what you've got initially, and then there's going to be some sort of change, and then we get to equilibrium, and that would be maybe one of these Ks. You know, there's a ton of different Ks that you could use, but those are all when things have kind of appeared to stop moving. Q is, there's going to be some movement away from Q to get you to K. So if we're talking about like the ice chart, these numbers are going to be like your Q, and this would be like your K, because this is when things have appeared to stop moving, and this is like just what you had at first. It's usually what the scientists mixed together, and then they saw, did the reaction go to the right or did it go to the left? So this part of the video is where I talk more about K equilibrium in terms of the math and the calculations a little bit. In the prerequisites, I did already explain a little bit about K equilibrium conceptually and definition-wise, so you might want to go back if you didn't watch that part. In general, K is a relationship where we have some products and reactants, and K tells us how much we have of them relative to each other. So if you've got like a really big K value for a reaction, that means that it's going to make a lot of products and not have very much reactants. If you've got a very small K, that means it's going to have not very much products compared to its reactants. So it's a ratio. It tells us which side is more stable and kind of how much more stable it is by the amount of stuff that is there, because the more stable side should have more matter being there, right? So if we look at this reaction, and it should have these backwards and forwards arrows because it's an equilibrium problem, and we've got a reversible reaction. Let's say that we have 2A reacting with 3B, and it makes 5C and 1D. So these are our products on the right side and reactants on the left side. Now, normally you're used to probably seeing this written like that. I want to show you this expanded form because it helps you understand what's going on with like the x's and how they're being squared or cubed sometimes in the ice chart. Because yeah, you've got 2A, and it may look like you've got 2 reactants, but in a sense you have like 5 reactants. 2 of them are A's and then 3 of them are B's. And same in a sense you have 6 products here, and there's 2 different types of substances that are the product, but you've got like 2 molecules of this combining with 3 molecules of that, to produce 5 of these molecules and one of those molecules. So when we talk about K equilibrium, it's really thinking about it more in terms of like an expanded form. It's saying how much product to reactant are there, and you need to multiply each one out. And so it's the way I think about this is like if you were to like change the amount of A that you have here, like for example, if you doubled the amount of A that you have in a situation, you've now doubled up 2 of your products that you have. So you now have like 4 times as much product. And so if you were at equilibrium, now you've got too much product and you've got to make some of the reactant, or vice versa. If you've got too much of the reactant, you're going to need to make the product. Okay. So the reason things are getting kind of squared here, like if you had like this was like 2x, then you're going to have like 2x times 2x, right? So that's the 4x squared that you normally see in these problems. And it's coming from the fact that you haven't doubled one of your reactants. You've actually doubled 2 of the reactants when we think about those reactants in terms of like um, molecules that are being used in the reaction, right? No, that got completely messed up. That's going to bother me. Okay, so it's also really important when you're talking about scientific notation to recognize how that relates to bigness and smallness of a number. Like being able to look at 2 times 10 up to the third power or 3 times 10 up to the fifth power and recognizing those are big numbers is going to be critical for these types of problems. Same with seeing if you had like uh, 1 times 10 up to the second power or 1 times 10 up to the negative ninth power. You're going to need to know that those are very small numbers. And that's going to be critical for working with these types of problems and thinking about, well, is this a small value or a big value and what's kind of going on there? If you have the product and reactant equal each other in this mathematical problem, and K is equal to 1, that's pretty rare though. It's kind of a bizarre situation. Now, it's also worth thinking about what happens if you were to plug in 1 or 1 molar, 1 atmosphere for all the chemicals. It doesn't matter what the equation is, the K value should come out as 1 if you plugged in 1 molar for everything. Like I could have a different reaction that has different exponents on it. Like maybe this I've changed from 3 to like 7. If it's 1 in here for everything, it doesn't matter how many 1s I'm multiplying by or dividing by, the whole thing should be equal to 1, right? So if you imagine that situation, like K is equal to 1 is like being at equilibrium, and then you doubled things up, like you have 2 molar or 2 atmosphere, you're no longer at equilibrium. Like if like you had some reaction at balloon and you squeeze it down, and now everything's twice as concentrated. If you were to go in and plug in 2 into everything here, because you have different numbers of exponents, they don't really cancel out. Because you're going to have 5 2s and 6 2s. So it's like 6 2s on the top and 5 2s on the bottom, right? And so they don't cancel each other out exactly. And so in that case, like you'd get 2 as your calculated value. So if we did actually do this, our Q would be too big. And so we need to make some more of the reactant. So it would be like, okay, well, now we need to make some more reactants. And that kind of is Le Chatelier's principle, where it's like, oh, well, if you squeeze things, you're going to need to make more of the more compact side, right? So that's another way of connecting Le Chatelier's principle and these molarities and the numbers. I also like to think about, well, what if K is equal to 1 and everything else is 1, but A is like a little too big, right? So maybe this is actually going to be like a Q value. So let's say that it should be at 1, but not everything is at 1, right? Like we've got too much of A. And so like our Q value ends up coming small because we've got too much product. And so we're going to need to make more reactant, right? And so it's going to shift to the right. And so in this case, you should see like a minus x and a minus x and a plus x and a plus x. See, I'm building up to the ice chart. Don't worry, we will get there. But that's kind of like the idea where it's like, oh well, there's too much of this reactant, so we're gonna need to get that and turn that into some product, right? I think I talked about this. I might have actually skipped over it. Q, when we're talking about that, that's very similar to K. Yeah, I think because I wrote it off to the side here, Q is not at equilibrium. These are like the initial conditions. So it's related to like this K equilibrium stuff, but it's like usually like the start. And it's like, okay, you're starting here and we need to end there. And how far do we need to go to get there? Right. So if we've got like we know it should be one, but these numbers are a little bit too small. If you look here, the Q value is too big, right? So it's like, okay, well, I have too much product to compare to reactants. I'm going to need to get rid of some of that. I'm gonna need to make this smaller. Like there's some amount that we're gonna need to take away from here and give to there, and then we would be at equilibrium, right? Now calculating that exact X can be a little bit complicated, but they usually give you ones that are like the easier math problems, even on the AP test. This is, I wanted to just highlight though, the most common mistake. And it has to do with the solids and gases and all that. So it's really important for understanding K equilibrium, that when we do equilibrium problems, we're only really looking at the things that are taking up space. So if we have like this is a problem that I went over with like a student I was tutoring, and there was this solid that's being added, and then it dissolves a little bit, and there's a little bit of that solid still there in the bottom. And we had been accidentally including that initially, like in our concentration, our ice table, but that really shouldn't have been the case, because you don't include solids. You only, if you're talking about concentrations, it's the ions, because ions are competing for space in solution. The solid that's fallen out of solution, it doesn't matter how much you have of that. The ions don't like see or interact with more product if you have more product. They reach that point of equilibrium. They've dissolved as much as they can dissolve, and then they stop. And there's got to be some solid on the bottom. So it doesn't really matter what number you have in here. You're gonna minus x, and it's gonna come out as something, but we don't include it because it isn't competing for space. And when we're talking about stability and how much of the product and reactant there is, we're only really interested in the things that are competing for space, because the more stable thing will take space from the less stable thing. So we only include gases when we're talking about like gases competing for space. We don't think about liquids and solids in that situation. And then when we're talking about ions in a liquid, you're only interested in other ions in that liquid. It doesn't matter if there's some solid there it's in there. It doesn't matter that there's a ton of water around it. Like you could try and put in the calculation for like the concentration of water, but that doesn't really make sense to do. It's just kind of a weird thing because it's not an ion, it's a liquid, right? So what ends up happening with these types of problems is that you end up having calculations where there's nothing in the denominator, nothing in the reactant side. So whenever you're doing like one of these KSB problems, there's not going to be a denominator if the that solid is the only thing on the reactant side, which it almost always is the only thing on the reactant side. There is also like if we're talking about gases, like if we have this gas right here, or this reaction right here, and we know that there's 15 torrs of water vapor and a total pressure, you can use a little bit of information to figure out like, oh, okay, well, I can figure out how much H there is. It's going to be the 36.3 minus 15, right? So I'll just kind of show you the idea behind these one real quick. This one isn't an ice table, so we're just kind of writing out the K value for the gas. So then it looks like we've got 21.3 torr H2. And the problem that I read was saying that this was, I think it was like 1,500 degrees Kelvin. So it's totally okay that water is a vapor. It's a gas in this situation. And these are solids in this situation. The only other gas in here besides the water vapor is the H2. And so what we can then do is we can say, well, K equilibrium is going to be my products over my reactants. And we can then say, okay, well, what are my products and reactants? It's only really this guy and that guy, but they actually are being cubed or brought up to the fourth, not cubed, brought up to the fourth power. And so we've got like concentration of H2O. That's up to the fourth power, it looks like. And then this is H2 also up to that fourth power. And so the K equilibrium here ends up being dependent on those powers, right? Like these don't cancel out. That's not how that works. You could plug in the numbers and see that for yourself, though, if you don't believe me. So in this case, these are actually cubed, not squared. H2O was 15 torr. And then this R was 1.3 torr. And we should be able to calculate that. So if we've got 15, oh, this is where I'm like, oh, I haven't used this in a while. 15 up to the fourth power. Oh, 5, yep, something like that. And then that, what was it? 21.34. And then raise that up to the fourth power. Oh, wow, that's a big number. Okay, so you can see that this it's a pretty small K value, even though these two things, they look like they're similar amounts, right? And so it's super important that you plug them in with the numbers, then you do your exponents, and that should be able to be simplified. Okay. I don't think I'm actually gonna solve that number. I'll put that as an interactive question for my interactives. Okay. There's a small error though. I was just double checking that. I totally messed up the H2. That's the product. The H2O, that's the reactant. And so these guys should be inversed. I did the K equilibrium for the opposite reaction. And so if you do that correctly, then you should be able to get something. I think it's about 4-ish. And so you can kind of double check using some guesstimation. Like, yeah, it's about 4. But then you can check the exact number on my interactive version of this video. Okay. But that is how you do those types of problems. Okay. Make sure that you're putting the actual correct thing in the correct spot. That is a easy to make mistake. So this is a FET simulation. I really like it. It's good for helping you kind of understand what's going on with equilibrium. So if we just have this, and let's start off with just 10 and 10 molecules for our two sides. And let's make it start kind of hot, but maybe let's make it a little bit warmer. So you can see that in this reaction that there's the reactants and the products, they've got A and B, and they're just generic forms. And there's a little bit of this hill that they've got to get over. And they all just randomly get a little bit more energy, and some of them will get enough energy to go over that hill. And some of them that get enough energy to go over that hill stay on the side that they're on. And some of them that get enough energy go to the other side, right? Just like that one did. It had enough and it hopped over to the other side. So that's basically what happens with equilibrium. There's a rate that goes forward and a rate that goes backwards. And it's basically dependent on how likely that thing is to have enough energy to get over this hump in the middle. You can make, like, if you see here, this side's more stable, so it should have more of the stuff on it, and that's what we're seeing right now. You can slow this process down. You can essentially make like slower reactions have a higher activation energy, is what it's called. And um, in theory, there should be more of these things on the side than on that side, but we don't really have enough energy to actually have that happen at a reasonable rate. We can add in a little bit more energy. It looks like now we've got enough energy for some of these things to get over this hump. It's going to be kind of slow though, but they should get the right ratio of the K to the R. So it's all kind of, this is the speed, and then their energy levels kind of determine um, how much is in the reactant side and how much is in the product side, right? Now, you might ask yourself, well, what's going to happen if I make these two have the same amount of stability? Ask yourself that. What's going to happen to the relative number of these things? Well, they should be approximately equal to each other, the products and reactants. If they have the same amount of stability, they're going to take up the same amount of space, and therefore you should have the same amount of these two different compounds. Now, if I take this reaction and I make it so that the reactants are favorable, as you can see, more of the atoms are going to be reactant side than product side, right? So that's kind of conceptually what's going on, is that they've got to get enough energy, and if they do, they'll go to the other side, and there will be more of them on the side that's more stable. It's just kind of a competition about which side is actually more stable, right? What else did I wanted to say? Yeah, I talked about the speed of the reaction, the activation energy. And then also you can kind of see that the rates, like how much it turns into the other stuff, kind of depends on how much there is. Like if I make there be a ton of B all of a sudden, at first the rate's gonna be pretty quick, right? It's gonna start turning into the product fairly quickly, and you can kind of see that it's doing so fairly quickly, and then it should slow down over time, right? So the rates are very much dependent on how much stuff there is, and they'll be very fast if there's more of the stuff, just because there's more of them getting the opportunities to go over, until so many of them have gone over that you're actually getting these coming back at the same rate, and then they kind of find that equilibrium. These look pretty close to each other. There should be more A than B though. It looks like, yeah, looks like we're getting a little bit closer to our ratio. That it looks like it's about a 2-to-1 ratio, almost something like that, that this gets nice and stable now with that new equilibrium. Kind of weird, right? So you can see that, yeah, I think that it's not 1-to-1, it's not 2-to-1, it's somewhere in between, and it's around there that we would reach equilibrium. This is a computer model, so it's kind of fluctuating a lot around that equilibrium. In real life, it's going to just stay at the same point, and you're not going to really see the changes that much. But you can kind of see what's going on there with the forward rates and the reverse rates and their relative stabilities, right? Okay, I think that was everything for the sim. Kind of short, that one. When we're talking about equilibrium, a lot of problems involve ice charts, and most of those are going to have what we call a negligible x, a very small x. That makes the math super, super easy and lets you do some mental math. I did want to highlight that according to some AP chemistry teachers online, the AP test may not require a calculator for or it's going to give you the option to have a calculator on the multiple choice questions. So they should still be able to be done using mental math, and it would actually be quicker, a lot of them doing mental math, because you got multiple choice options. Um, and I'm going to still teach it from that perspective. Yeah, you may have a calculator to do some exact calculations, but these problems are way, way easier if you just do a little assumption. So basically, you need to look at where Q is and figure out, okay, most of the time with these problems, it's like all reactant, and then it's gonna turn a little bit into the product. Uh, and it's like we don't need to really calculate Q. It's just Q is basically, if we're talking about product over reactant, it's basically zero because there's like no product. And then there's some sort of product that's made, and it's going to form a small amount of products because it's got a small K value. So these will have a small K value. Very, very common. When we're talking about ice, what that really stands for is the time that we're talking about. So there's the initial time period, and then there's the final time period or the end point or equilibrium. I've seen this be called the end or the equilibrium point. So you've got like basically start and finish, and then what changes between the two, right? And when I'm saying finish, remember the reaction is still happening forwards and backwards. It's just equal and opposite rates, and they cancel each other out like if you're running on a treadmill, right? So there's no more visible change at the end. There is some initial point. Usually it's all reactant, and then there's some change, and then we're at that equilibrium point, and we need to calculate maybe a concentration or a K value. So in I've got some worked out problem here that I'm going to talk about, and then I'll show you what this means in the next one. So if we look here, this one first problem, let's say that K is very small and X is negligible. So maybe you have a K value of 10 up to the negative 18. And so we're looking at this and we're like, okay, this is a very small K value because it's negative 18. And so it's mostly reactant. Some of it will turn into the product, but most of it's staying reactant. Oftentimes they give you 1 molar, especially if it's an easier problem. If it's like a general chemistry class, they usually start with like 1 molar. But this might not be 1 molar. So you have to be a little bit careful to see what your initial conditions really are. But in this case, I'm just telling you that we're starting off with 1 molar. So we've got our initial, and you've got our different reactants and products that we write. And so we would write this out kind of like so that you have the chemical and its corresponding amount or change underneath it. So we've got our reactant HA and our products H plus and A minus. And in this case, we can say that X is going to be very, very small because K is very, very small. We know that ultimately this is going to be a small number and this is going to be a huge number. And if that's the case, if X is very small and this is very big, then 1 minus X is going to be 1. We can estimate that. So the idea is that you can get rid of this X if it's small compared to the initial amount. And that is done if we've got a small K. And then it's pretty easy because you've just got a square root that you can work with. So this might also be like, oftentimes this is like 2x squared is equal to 10 up to the negative 18. And so it's just like, okay, in that case, you would divide by, maybe it's like 4x squared. Maybe you divide by 4 and then do the square root, right? But this should be something that's pretty straightforward. You get rid of the thing that's small, and then you just square root what you have left. And as you can see, X is 10 up to the negative 9. So as we suggested, X is negligible. Because if we said 1 minus 1 times 10 up to the negative 9, if you want to do that on your calculator, you can. But this is literally like the same thing. Or it's virtually the same thing. It's not literally the same thing. They're so close. So we can get rid of that, and we can say that that is equal to 1. And our X values we can then plug in here. And as you can see, that was correct. So my assumption that it was negligible is correct. If you're able to double check and plug in the numbers and it gives you the correct K value, then you're good to go. So that's the main idea with these guys is if it's a small k, just drop the x, right? So this is a slightly different example. We've got a different reaction, different K value, and a little bit of info there. So they've told us the mole of the substance as well as the volume that we're putting this in. We have to do the concentration, so it's moles and liters. So if we look at this problem, they gave us, it looks like 1 mole and 2 liters. So we're going to need to get that and then plug that into this ice table. You have to do an ice table. I had a student I was tutoring that skipped that, and then they just wrote out the expression, and they would make mistakes because of the stuff that they didn't write out here. It's worth taking the time to slow down and do that. So if we have, it looks like 1 mole of this stuff, and it looks like 2 liters. This is going to be 0.5 molar. That's the concentration. Because remember, these things are competing for space, we want to know what that concentration is. So we've got 0.5 molar. And it looks like we don't have any of these two things. Now, if we take this and we want to make it into some of these guys, because we should have more than 0, we're going to need to think about, well, if I use up 2 molecules of this, I produce 2 molecules of that and make 1 molecule of this. So if I use up 2 of these molecules, I produce 2 of these molecules, and I also produce 2 of these molecules, right? So we end up getting 0.5 molar minus 2x. And we get 2x and 2x right there. And this is where, like, my student, I think, would have messed up. They might have put like 1 molar instead of the 0.5 molar. So we've got K is equal to products over reactants. I always write that in because I need to know what goes where. As you've seen before, I can mess up what goes on the top and bottom, and that's gonna throw me off. So I can't do that. Actually, before I plug in the numbers, I realized that there's one other thing that I kind of skipped, which was writing this out with the concentrations like so, without the actual numbers in. That's squared because there's 2 of these, because remember, it's like NaCl times another NaCl. And then we've got NO squared because it's NO times Cl. Something like that. Okay. All right, we're getting there. Don't worry. And then we've got our top. Something's getting squared, and then something's not getting squared. It's just up to its first power. Okay, so it looks like we've got 2x. And I think I actually, yeah, this is not going to make 2x. Going to make 1x. Okay. That's why it's good to double check yourself on these things. So as you can see, I kind of paused and I was like, wait, no, that shouldn't be 2x. That should be x. Because if you use up 2 of these, you're actually only making 1 of those. What we can say here is, because k is very small, remember that right here, we're like, oh, this is very small. We can say that the amount that will turn into reactant compared to product is going to be very small. It's a negligible amount. We can cancel out and get rid of it. And so this ends up being 4x squared times x all over 0.5 molar. And if you combine that, that's going to be 4x to the cubed power, and then this is 0.5 molar. And we knew what the k value was, so we should be able to solve for x. So this was it was 10 up to what power was it? 1.6 times 10 up to -5. So I've got that equal to the k. And I should be able to now isolate for x cubed. So in K, usually you don't give units because it's different units with each time. So it's just like a convention that we don't write that in. And then we're going to have to cube root whatever we end up getting from that. So let's go ahead and see what we get from that. Calculator 1.6. Well, it's actually got to be times 0.5. So that's actually the same as like 0.8 times 10 to the negative 5. Or is that 8 times 10 up to the negative 4, I think. Yeah, you could check that on your calculator if you wanted to. You could do 1.6 times, what is it, 10 up to the negative 5, right? And then that times 0.5. Yep. 1, 2. Oh, actually, I messed this up. It should be up to the negative 6. Yeah, make that bigger. That needs to get smaller. So we need to cube root that. So if we cube root that, take that, gosh, how do you do this? Up to the third power, I think. Yeah. I'm not sure if I'm doing that correctly, but I believe that x is equal to 0.02 or 2 times 10 up to the, yeah. And if you look at the cube root, that does actually kind of make sense if you know how to do your mental math on some of that. Okay. So that's the kind of the easier ones. And 2 times 10 up to the negative 2, that's going to be the x value. And so you need to take that and kind of plug that back in here. So the NO at equilibrium was equal to 2x. So it's 2 times whatever we got there. So we got 4 times 10 up to the negative 2 NO. And then the Cl2, it's just x. And so that's just going to be the concentration of that guy right there. And we could plug this back in and we could double check that. So we've got our different concentrations because we've got the 0.5 molar, which was that amount of reactant, right? So we're basically taking this right here and kind of plugging it back in. So we could take our different concentrations because we got our concentration of reactant, and these are our products at equilibrium. And it is a pet peeve of mine, so I do like to write in what it is that I'm talking about. This is the NO2, NO, and this is the Cl2. And that this was the NOCl, right? And so we could then plug these back in, and they should be equal to the 0.6 times 10 up to the negative 5 power. Okay. So you can double check that, and you should be able to see that. But to save time, I'm going to cut that out here. Most of the time you would use an ice chart, you would have a negligible x, but there's a couple situations where the x is significant, and there's a couple tricks that I'll go over to help you understand it. We're going to start with the most common one, which is when you have a very big K, and it's basically there's some flow that goes back, but it's insignificant, so we don't have to think about that going back at all. We just say it goes fully forward, and it's pretty easy, those problems. Then there's also sometimes they'll give you like the percent of the stuff that has decomposed, and you then have to use your actual x value and find the k. And so there's a significant x there, and they've given you it, and now you need to find the k. It would be very difficult to go the other way, but going this direction is fairly easy. If you have x, you can plug it in pretty easily. And then there's another one. This is something that you see like in your college textbook where they do guess and check, where you have something where it's significant and you know what your k value is, and you know that the x will be significant, but you're not sure exactly what it will be. You basically guess and check. So you kind of look at the numbers, plug in something that looks close, and then see what you get for your x value, for the second x value. So you've basically determined what x1 is, and you're saying what would x2 be, and you want them to actually be close to each other. So in this case, when we plugged in 44, the x came out bigger, so we needed a bigger x than what we had. So we tried 55. That got me a little bit closer, but it was it like wasn't quite right. So I tried 63, and that wasn't quite right. So we tried 60, and then 57, and then 59. Eventually we got to something where the x value that we were guessing was what we were getting out from the second x value. So it's kind of a weird one. You're probably not going to see that, so I'm not going to even spend time on it. And then this is pretty rare, but sometimes there's a nice clean square root on both sides, and this happens if you have like two reactants and two products and they're both being squared. And so in that case, you can square root both sides and then simplify by distributing the k. Again, pretty rare that you would actually see that, but it is doable. It's kind of nasty though, to be honest. Um, and you can see like the example problem that I picked right there. There's one gas, two gas, and they're forming two gases as well, I believe. And so it's like two things formed and two things used, and so they kind of can cancel out in terms of those exponents that we have in that problem. But if we wanted to actually look at these guys, let's say that you have a problem like this where um, there's, sorry, the problem that I copied over got kind of messed up. So they basically told us like, okay, there's this reaction. We have a K value that is very large. And so we know that this is going to have a significant amount turn into product. If it's that big of a K value, I'd just say all of it turns into product. And so if you think about the ice chart, it's kind of weird. I'm actually going to line up the ice chart so it's just underneath our reaction because that just works out nicely. And so it's like, okay, well, you had, what was it, 36.1 atmospheres for the pressure of this thing. And then there's 2x, it's like plus x and plus x right there. Okay. This is going to end up being 0 because all of it will end up getting used. And then x ends up just being a little bit of an algebra problem. So 36.1 minus 2x is equal to 0. You can see that this is going to be, I think it's like 18.1, or it's like 18.5, I think, actually, would be what you'd get from, or at 0.05. So that's what we get for our different x values here. And I think, yeah, they had rounded it to the 18.1. And so you get those two different things. In reality, this isn't actually at equilibrium. In reality, there's a slight amount that goes back. Okay, but that amount would be pretty insignificant, and it doesn't really. You can calculate this number. It's just going to be so close to 0 that we can say it's effectively 0. And so you could end up doing your like 18.1 minus y, but it's negligible. 18.1 minus y, but it's negligible because we do have a little bit of product here, technically speaking. If we were to look at this, it would be the 18.1 squared all over whatever this y value is. Um, it's it is kind of weird, but you can kind of go through it and think through it like that. What you would find though is that that y value is close to 0, so we don't really even do that, right? Typically, we don't do that. So if you have another problem, let's say we've got this bromine and chlorine, it's turning into their gases. And if we look at that, it looks like they've given us the moles and the liters. So remember, we need the molarity. If they've given us, it looks like 100 mole of that reactant. And then we've got our, sorry about that, where was I? Oh yeah, so we've got the molar, we've got our liters, so we've got our 2 liters. And our concentration right here would be 0.05 molar, something like that, of that substance. Okay, so we've got our initial concentration there. Yep. So it's kind of weird. They're saying pressure. Actually, yes, if you look at this problem, they have given us everything like the volume, the moles, and the temperature to find the pressure. So we can do that. It's just a little bit of work. So I'm just because we're not doing gas laws, I'm going to do that calculation and then just give you the answer. Okay, here we go. I believe that that is what we get for the pressure of the reactant initially when we had that gas in that container. So that's part A. We've got that done. Because it was a gas, it wasn't this concentration, so that part did not apply. The expression for K equilibrium, this is just the same as for any K value. It's going to be product over reactant. And so we need to think about what our products are. It's going to be that Br2, and it looks like chlorine 2, chlorine gas and bromine gas, I believe. And then we've got the BrCl, and that's getting squared. Because remember, it's like we have 2 of these things. It's one of these plus another one, and so it ends up being this times another one. Like these get multiplied. We need to multiply the 2 reactants that we have present there. So that's part B. That's our K equilibrium. And then let's say 42% originally has decomposed. Oh, that's lovely, isn't it? So we had an ice chart. And I'm just going to rewrite the reaction here. So, and we started off with, it looks like these were atmospheres. 1.22 atmospheres, and 42% of that is going to go. So it's going to be minus some number. It's going to be 2x because every two of these will be used up for every one of these that are made, and same with every one of those that are made. And so we end up getting some sort of unknown number. And then this is going to be whatever is 42%. So 1.22 atmospheres. We're basically saying what is going to be, what is it, 42% of that number. And you can do that by multiplying it by 0.42. So you can have 1.22 times 0.42. And that would be something like that. So that's how much is being used. Okay. And if you wanted to just double check that, you could say 50%. So it's like 0.5. And you could say this is 1.2. right? So yeah, this seems reasonable given that number. So 42% of this has decomposed, I believe they said. Yeah, 42 has broken down. So that is how much is gone, how much we used. So 0.5124 atmospheres is equal to how much we used up, or how much is gone. So that's equal to the 2x. That was the change. So then we can say x is going to be equal to that divided by 2.2562 atmospheres. And that looks like that should be our x values for these guys. So it looks like 0.2562 atmosphere there, as well as also going in there. And then this is going to be whatever it is minus that number. So 1.22 minus 0.5124. Okay. 0.7, what was it? 0.076. So that's a 0. Okay. So if they said after the, yeah, so 42% of it is decomposed. All right. And so we should have all the values for this now. I'm just also gonna make sure that I write that in just to follow those conventions. Okay, so K equilibrium is equal to, I'm just making sure that I plug in everything correctly. I want to make sure I square that because I know I'm going to forget. So the concentration is the bromine, which was the 2562 atmospheres of bromine. And I'm going to write in my substance just because it's good with the exponents to always just do that. It's a habit of mine. 62 atmospheres of chlorine gas. Yeah, these are both gases. And then something is getting squared. It's the 0.7076 atmospheres of the remaining BrCl. And that, I believe, is what you would get. And then you need to just plug that in. It's a awful thing with the calculator. I'm gonna just do my top and then my bottom. 0.256. See, that's what's gonna mess you up, right? That and times itself. Okay, that's top. And I would always kind of slow it down on these problems and do it piece by piece instead of trying to do it all at once, because that's where most calculator mistakes end up happening, is when people try and do too much math at once. And we get 0.500. Okay. And so we get, what is it? 0.065. I don't know. My sig figs are all messed up right now, because these numbers I had been running out to like 4 sig figs. What did they give us originally? Three sig figs. So our answer should be accurate to 3 sig figs, but I should write more than what I have right here. What did I get? 0.38. Yeah, let's include the 3.8 and 5. Where is it? 6.9. Yeah, that should be enough sig figs for us to be able to simplify that down. Okay, and then we get 0.13. I think there's only 3 sig figs, so we can round that to 0.131, right? I believe that that's that for that part. Okay, so yeah, these other ones, I briefly showed them earlier and talked about them, but we're not going to go through them. Usually the unit after equilibrium is going to be acids and bases because they're a type of equilibrium. So you'll often have these like acids and bases on the opposite side of reactions from each other. And it's kind of a little bit confusing about the Ka, Kb stuff, but I just want to relate it to what we were talking about with the ice chart. So big picture on this, you're gonna have small K values if you're working with a weak acid or a weak base. If you're working with a strong acid or a strong base, you just wouldn't have a Ka value because it's going to 100% dissociation. So you would have a lot of these things where you're doing a negligible X. This is very, very similar to what I was talking about in this part. I was talking about those negligible X's. And you see that it's basically the same thing. It's just got the format of your protons and the conjugate base and the acid, and then you've got your Ka for that. It's the same sort of thing. There's some negligible X. We can get rid of that from the calculation, and it's not too bad. There is also, this is the weak acid. You can look at the weak base as well and look at the reverse process. So this is also a conjugate. So the weak acid has a conjugate that is a weak base. So if you have like one, if you look at this thing right here, you can look at the equilibrium and look at how much OH you have as well by looking at its equilibrium. And you can plug in the numbers and it should work out. It's kind of weird. And this can also be related through that H and OH if you wanted to. It's kind of, as I said, kind of bizarre to do that with this problem. But these acid-base problems are essentially equilibrium problems, but the reactants and the products that we're using are acids and bases. And it's almost always going to have a negligible X unless you don't need to use an ice chart because it's just going to be completely dissociated. Okay. All right. That's it. That was a long one. Thank you for joining me. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.